Okay, so let's continue on. So here it's going to be, once again, we have to ask questions. Is it permutation? Is it combination? Do we have an and, which means multiplication? Do we have an or, which means addition? So a corporation has 8 men, 6 women on its board of directors. At a stockholders meeting, 7 members are seated in a row on the platform. The directors are chosen and assigned a seat. Okay, so they're chosen at random and assigned a seat. And notice that each member is a different person, correct? We have Alice, we have Bob, Cindy, etc. And so we have 3 questions. The first question is, what's the probability that I have 3 men sitting together and 4 women? So there's a special placement, specific placement of the men, a specific placement of the women. And notice that the directors have different names. So this is not like the tomato problem where we can distinguish. What's the probability that we put a male, a woman, man, woman, man? So in other words, we're alternating. And then the third question is, what's the probability that we have 3 men seated together and 4 women seated together? Now, wait a minute. Isn't this question C the same as question A? There's 3 men. There's 4 women. There's a difference between problem C and part A, though, because this here we have the first 3 seats are men, then the next 4 are women. But we could reverse this. We could put women, etc., and then men. So this question is not the same as this one. So be very careful about the wording of things. Is order important? The answer is yes, because these are different names of people. Remember the horse racing problem? So if I have John, Andy, and if I switch those, that's not the same in this situation. So that means permutation. Now, what is a sample space? Well, we're told we have, 8 men and 6 women. So we throw them in all together. And so the size of the sample space is, we have 14 people and we're choosing 7. So just go ahead and do the calculation and we come up with this big number, 17 million, etc. Now let's take each of these individually. So the first one said, I want to have 3 men, and n means multiplication. I want to have 4 women. And the order is important here. We have different people's names. These are not tomatoes. These are actual people. So we have 8 men available. We're picking 3 out of the 8. We have 6 women available, and we're picking 4 out of them. So if we do the calculation, 8 factorial over 5 factorial, remember what you're going to do is 8, 7, and then stop it at 6 and cancel the 5 factorials. And then we're going to do the 6 choose 4. So 6 minus 4 is 2 factorial, 6, 5, 4, etc. And then divide by 2, you get 360. Now remember, this is the 3 men and 4 women, you multiply. So when you multiply the 336 times the 360, divide by this, do your simplifications, and we get 1 out of 143. Okay, the next one. Now here we have specific placements of it. We want a male, a woman, male, woman, etc. So we're alternating. So we can just use the multiplication principle directly. How many men do we have? We start with 8, correct? Then we have 7 left. Then we have 6 left. Then we have 5 left. So what I'm doing is I'm filling in the male portions. Now the women, we start out with 6? The next one we have 5 left over. Next one we have 4 left over. So we multiply all this stuff out, simplify, and we get 5 out of 429. The next one, part C. So we have to be careful, because when we say 3 men and 4 women, we could have the men here, the women here, or the women here and the men here. Or means what? Addition. So we have to go, this has to happen and this has to happen, which means multiplication, or, which means addition, this has to happen and this has to happen. So it's the same thing. We have 8 men available, we're choosing 3. We have 6 available, we're choosing 4. We multiply those two. Here, notice it's the same thing. So there's actually two ways of doing this. Having the men go first, followed by the women, or the women go first, followed by the men. And so if we go through all these calculations, we have twice these numbers, so you go through your calculations again, and you end up with 2 over 143. So there were quite a few steps to this problem. Excuse me. A branch office of a corporation employs 6 women and 5 men. If 4 employees are selected at random to help open a new branch office, what's the probability that at least one is a woman? Now, first question, is order important or is not? Notice that you don't care. There's no specific positions like the seating was in the previous problem, correct? So this is going to be a combination type of problem versus a permutation. Now, what's the probability that at least one is a woman? All right, so we have to have 4 employees. Now, what do we mean by success? The probability that at least one is a woman. So what we're going to have to do is list out all the possibilities that can happen. So there are 5 men available and 6 women available, and we're picking what? 4 people. So we could have all 4 are men, none are women. 3 are men, 1 are women. Notice it's the same kind of thing that we did with the tossing of coins. 3 heads, no tails. 2 heads, 1 tail, etc. Right? So I have 4 people going. All of them can be what? Men, none women. Or 3 men, 1 woman. 2 men, 2. 1 man, 3 women. No men, 4. Now what do we mean by success? At least one is a woman. So this is not true. That's not. This works, this works, this works, this. That means these possibilities here are success. This one is considered failure. Now, if you were to do this directly going success, you would say this has to happen, or this has to happen, or this has to happen, or this has. You'd have to do 1, 2, 3, 4 different calculations. Now we're going to use the idea of a complement. The probability of adding all these up has to add up to be 1. So, in other words, if I take failure and I subtract that from 1, I get these probabilities. All right, so order is not important. All we care about is having people. We don't associate names with them. We have 11 people, and we're choosing what? 4 out of the 11. Combination. So, as I mentioned, success means one of these has to happen. In other words, 3 men and 1 woman, or 2. Now look, if you did this, you're going to have to do 4 separate calculations. The probability of making a mistake is really high. We are just going to calculate what the probability of this is and just subtract it from 1. So here's what we do. We say failure means 4 men and 0 women. So and means multiplication. So if we calculate 4 men out of how many available do we have? Which was what? 5 men. So what we do is, to get this guy, we're not going to go through all of this. We're going to say 4 men out of 5 and 0 women out of 6. So this is the probability of failure. So I am not going to do this one, or this one, and then add those up. That's 4 times the chances of making a mistake. Too many calculations. So we're going to say, what's the probability of failure? Subtract that from 1. And that saves us doing 4 separate calculations. So I say, in this case, failure, 1 minus that. So here we're using the idea of the complement of the set. This is what we want, but if we calculate this, we only have to do 1 calculation, subtract it from 1, and voila, we're done with that. Let's take another example. So here we're going to go back to Venn diagrams. So we have 200 students total. 40 take English, 50 take math, 10 take both. So in other words, there are some students that are common to both of these. So what we do is we draw our English set and our math set. 10 are taking both. Now we had 40 English, so I have to subtract. Remember, do not double count. You're subtracting 10 from the 40 to 30. The number taking math was 50. There's 10 that take both. Subtract that there, you get 40. So that means, what does this 30 mean? It means those people are taking English but are not taking math. What does this 40 mean? 40 students are taking math, but they are not taking English. 10 are taking both. So if I want to know what the union is, I take 30 plus 10, you do not take 40 plus 50, you double count it. So 30 plus 10 is 40, 40 plus 40 is 80. Now if I want to know what's out here, if this adds up to 80 and there's 200, then I subtract 200. I subtract 80 from the 200 to get 120. Means 120 students are taking what? Neither English or math. So now I could start talking about probabilities. Okay. So if I want to know what's the probability that I'm taking English, I take how many people are taking English. So this includes both English and math, right? Sorry about that. Both English and math. That's 40. So I have 40 out of, what, 200? That's how I calculate my probability of taking English. How about math? Well, there are 50 out of 200, so 25% are taking math. English and math, that's the union, right? So that means we go 30. Please, do not 40 and 50. It's 30. You're double counting. So it's 40 plus 40 is 80. So we take, here's our 80 over 200. If we're saying both, that means you're the intersection. So that was, what, 10 out of 200? So that's 1 out of 20. So that's how we calculate probabilities using the Venn diagrams. Okay. We're going to finish off with this one. In a remote jungle village, the probability of a child contracting malaria is 45%. Probability of contracting measles is 65%. Probability of contracting both is 20%. And believe it or not, these numbers are not off that far. It's actually quite realistic. So we're going to draw a Venn diagram. So there are people that have measles. Some have malaria, measles. Please don't double count. You take the 45%. Some of them, 20% have both, so you subtract off the 20%. 65% have measles, subtract off the 20%, you're left with 45%. So when I go, these are the people that have what? Neither one of the diseases. So when I add up this number plus this number plus this number plus this number, it has to add up to be 1. So if I look at the measles or, this should be malaria, sorry, malaria or measles, 25, 20, and 45, so that is what, 45, yeah, 45 and 40, that's 90% have either one of them, which means that out here, there's only 10% that don't have either disease. That's pretty serious. Okay, so mutually exclusive events are events that are completely disjoint. They don't have anything. So suppose I tell you I'm selecting 2 people at random from 7 men and 5 women. These are 2 distinct things. So I could ask, what's the probability that both are men or both are women? Probability at least one is men. So in other words, what we're going to have to do is go back to the same type of thing. Is it and? Is it or? Is the order important? Is it not important? Okay, so both men or both women. So we're picking out 2 people. And you can't have both at the same time. I mean, this one and this one. This is what we mean by mutually exclusive. The existence of one means the other one can't happen. Order is not important. So if we put all the people together, 7 plus 5 is 12. And I'm picking out 2 of them. So the size of the sample space is 12, choose 2. And you can calculate that. Now, what's the probability of doing men, both are men or both are women? Now, what do we mean by or? It's going to be the adding. So we're picking 2 out of 7 or 2 out of 5. The size of the sample space is in both the same cases, so now you just do the arithmetic and we get 31 out of 66, which is roughly about, what, 50%. Okay, at least one is a male. Again, we have to list off all the possibilities. So if I have 2 people going, I could have no men and 2 women, 1 man and 1 woman, 2 men and no. So what do we mean by at least one is male? It means this one and this one are success. This is failure. We are not going to calculate this probability. We're going to calculate this probability and we're going to subtract it from 1. So 0 men out of what? 7 and 2 out of 5. So here's how we do the calculation. We calculate, instead of, so we have the probability of failure plus success. The problem is success consists of what? 2 events. So instead of calculating this, I'm going to take this and subtract it. So we take the probability that, so at least one was male. So we say both are women. How does that happen? We have 5 women. We're choosing 2. This is the probability of failure. We want the probability of success. We're using this idea of a complement. So we take 1 minus failure, gives us success. And then just simplifying, I get 28 out of 33, which is pretty close to 1.